So welcome to the another session on frontiers in CFD. So today we will see the CFD simulation of lithium-ion battery pack. So first thing what we will do is the prepare the geometry of battery pack with the design modeler tool which is available in ANSYS Workbench. Second thing we are going to do generate a mesh. We are going to give the name selection, and the third thing which we are going to do is apply the boundary conditions, and we will visualize the results in the post processor. So welcome you all. Today we'll see the CFD simulation of lithium-ion battery pack. So for that we are using the ANSYS Workbench, more specifically the Fluent tool. So first let's start with the Workbench window. We are going to make use of Fluid Flow Fluent. So click on it. So first of all we are going to prepare the geometry. So open the design modeler. So I'm going to create a small battery pack. This can be extended to a larger one just for the better understanding and to reduce the time which is required. I will want to prepare a comparatively smaller battery pack, and then we are going to do the analysis. So first of all, set the units. I will set it to mm over here. So first of all, let's create a primitive. Let's say it's a box. So let's have the dimension of the box as 92, and this one y component. Normally the height of the cell is around 65. So z component I will put again 92. X component I also have taken 92. Y component also have taken 92. So these are the dimension of battery pack. I will make it frozen so as to visualize it in better way. So this is how the geometry has been prepared first for your battery pack, and based upon this battery pack we are going to prepare the cells out of it. So first of all, go to create primitive. Let's take it cylinder. Now I want this cells to be in y component, so make it z component to be equal to 0. Normally the radius of the battery pack is cell is 9, diameter is around 1.8. so we can see right now it is here. I will just shift this to x coordinate. Let's say it's by 13. I will change the z coordinate to again by 13 over here. So you got the first cell out of here. Now instead of making add material, I will make it slice material, because we already prepared the box which will be like a battery cabinet. So I'm going to make it generate. So this is the first cell which has been generated. Now you can see in the other way also. Now I'm going to create such in n number. So one more time create primitive. One more time I will put it cylinder. How much? First one I have took it at 13. I will give a separation between them by a distance that is equal to 22. So here again I will put z component as 65. Y component as 65, z component as 0. So first cell has taken at 13. Now I will take the second cell at a distance of separation between them is 22. So I will put it 35. So here it will come. Z component I will put it as it is, the one which I have taken for this row. It will be I will taking the 13. So instead of making as a add material, I will make it frozen over here, slice material over here. Let's generate. So this is the second thing which I have generated. Now I will generate Okay, so this is a box dimension. Now I will generate the third one. So let's take it again as a cylinder. So again x coordinate I will increase by 22. So earlier it was 35 which is taken, now it will take it 57. Z component will be the same as the one which has been specified. Here y component you take it 65 and make it 0. Now this is the origin definition which is used for shifting the object from your reference axis, whereas this will define the dimension of object in a particular direction. So let's make it slice material and then we proceed with generation. Now one more time create a primitive, select the cylinder. uh, Now earlier we have taken 57, now I will take it 79. This one again will be as 13. Make it slice material over here. So y component to be equal to 65, z component will make it 0, and then the fourth cell will be generated. So this is how we have generated the fourth cell. Now same way we are going to generate it on the other direction. So one more time go to primitive, again take a cylinder. Now x component I will take it 13 as it is. Now z component I will take it 35 over here. So make it 65 in y direction, make this is equal to 0. So your object will appear somewhere here. Now make it slice, then make it generate. So this is the second thing which I have done. So similarly I will create one more primitive, that is a cylinder. Instead of okay, now earlier we have taken 13, now I'll take it 35, make this one again as a 35, and let's uh, make this as 65 and this component to be equal to 0. So this is how the cell is generated at this location. Make it slice material. So you need to carefully remember you have to make each and everything as a slice material. So one more time create a primitive over here as a cylinder, make it this as a slice material. Now x component I will take it 57 over here, then this will be 35 as it is, then this component will be 65, this component will be equal to 0. Let's make it slice and let's make it generate. One, two, three, and 4. This is 5, 6, and 7. So this is the 3 we are generated. One more time I will take it cylinder. X coordinate I will take it 79. Y coordinate Z coordinate I will make it 35. Let's make it 65. Let's make it 0. So let's select the option of slice material and generate it. So it is generated here. So right now we have generated 8. We want to generate more 8. So go on to create one more time as a primitive, as a cylinder. Make it slice material. So first of all you take it x component as 13, then z component you will take it as 57. Now make it y component as 65, this component as 0. Now make it slice material and generate. So one more object is generated. Similarly I will go with one more primitive, that is cylinder. Now x component I will take it 35, then z component I will make it 57 over here. Instead of add material I will make it slice material. Then here you need 65, here make it 0, and let's generate it again. So it will be generated here. So likewise I will generate the remaining. So let's take it 57, let's take it 57, make it 65, 0. Okay, so we have, okay, make it slice make it slice material and let's generate. So carefully remember each and every them should be a slice material so that we will be having proper boundary conditions at the end. So create one more primitive as cylinder. Instead x coordinate I will put it 13, z coordinate I will put it 79. Make it slice material. Instead of y component 0, make it 65, make it 0. So the object will be generated at this location. One more time, take a primitive. Let's take a cylinder, make it slice material. X coordinate I will make it 35 now, and this one will be again 79. Here make it 65, make this is equal to 0. So let's make it generate. So one more time I will create two more cylinder. Instead of making add material, we'll put it slice material. So this one will be again 57, this will be 79, this will be 65. Y component will make it 0. So again the third will be generated here, and last one we are going to generate, that is again as a cylinder. X coordinate I will make it 79, Z coordinate also I will make it 79. Here I will make it 65 and I will make this one as 0. So instead of add material, we'll make it slice material. So in this way, we have generated a battery pack which has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there are total of 16 cells which have been available. In addition to that, you may provide some inlet and outlet on this end. I'm not going to prepare it. You may prepare the same geometry which is related to maybe some inlet and outlet, but the whole geometry I will keep it as an inlet and whole geometry I will keep it as outlet. Now before proceeding, I will just make sure that which is my battery pack and which one is my the fluid zone. So this is going to be my battery pack. So I put it name as say battery pack over here. Remaining this one, okay, the battery pack will be your fluid zone. So I'll put it fluid 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 16. So I will make this as form new part. I will define this as say cell. So if you want, you can preferably name this also, say cell 1. Or you can do is select all and you can give the name also. Okay, so you may click rename bodies. I may put it cell. So everyone will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to 16. So likewise you can do. Now this is cell which has been generated. This is related to solid. The battery pack is actually fluid. Now you may save the work. Okay, go back to Workbench window. You may save the work as per your name. Let us suppose here I put it in some folder. Let's have, okay, so let's make it folder. So we have made a pack of 16 pack cell. Okay, give it a name over here, 16 pack or whatever the name you want. Okay, make it okay. Saving is important so that we can access the work later on. So the first part which is related to geometry creation is over. Now it's a time to prepare the mesh. So click on mesh. It will take some time to load. So once this is open, you will see the object which is in front of you. Just click on generate mesh. First of all, it will go on to generate default mesh. So if you are not satisfied with the default mesh, you can change the element size also based upon whatever the dimensions you had. Say for example, if I had put it 0.0015 as a element size, and let's generate the mesh. So depending on how fine you are making the mesh, the time required also will change. So if you are satisfied with this mesh, you can continue with it, or if you are not satisfied, you may generate a finer mesh than this also. So I'm going to go with this mesh because I'm just trying to do the analysis whether the things goes in the right way or not, so that we want to visualize. So now it's time to make some inlet and outlet. So I will put this as a inlet over here. So make it name selection, put it inlet. Okay, and on the other side I will make it the outlet here. So this is the outlet for the flow of fluid which is used for cooling. Now another thing is I need to select the cell walls, but right now it is not possible to select it. So what I will do is I will go back to geometry and select the battery pack, and I will make the battery pack to hide. Now I can select the internal faces. So I will select all of this internal faces on from all such directions. Okay, ensure that you have selected each and everything in order to proceed. So this was the last. So we have selected 16 faces. You may just check it and then create the name selection out here. So what I will put name over here is the cell boundary. So I have done three things: one inlet, and this is outlet and wall. So now you can show your battery pack. So this is now the mesh which has been generated. You have specified inlet, also you have specified outlet, and okay, yeah, this is inlet on this side, outlet on this side, and cell wall boundary on this side. Now make it update. So you will get a message that is a mesh translation to Fluent is successful. So if you receive this message, you can proceed further. Now if you want, you can close the mesh window also. Now let's proceed with the setup. So depending on how many processors you have on your computer, accordingly you can put it. Let us suppose if I am putting, in my case, it is around 16. Click on the double precision and let's click on the start. So I can run around 20 processes simultaneously, but I have put around 16 so that the system may not hang. So according to configuration of system, you can start with your the number of processors that you want to run it simultaneously. Again, this is with the student version of ANSYS has the limitation of 4. So accordingly, if you are using the student version, so you may put it 4. So what we need to do is we need to use the transient model. Then we need to specify the gravity. So gravity, we are specifying it in the negative direction. Here you can just visualize the things. Now first of all, I will put the model energy equation and we are going to turn it on. Then we are going to take K epsilon model, out of which we will select enhanced wall treatment, thermal effect, and the curvature correction. So we'll make it okay. So these are the only two model which we are going to look, because we are just interested in the thermal analysis of CFD thermal analysis of battery pack. So we have kept only two equations on. Now it's time to select the material. I'm going to select the air as a working fluid. Only thing I'm going to change is this one. I'm going to use, instead of the aluminium, I'm going to use the solid material as nickel, because more preferably when you consider the lithium-ion battery pack, the outer cover is actually outer layer of your lithium-ion battery is covered with the nickel. So we'll put it as a material and we're going to do the analysis. Okay, so we have set the material as air as a working fluid. Second one, we have put the nickel as a material for your cell. Now let's go for the boundary conditions out here. So where I'm going to apply the boundary conditions, I'm going to apply the boundary conditions at the inlet. Let us suppose if I put the velocity is around 0.5 meter per second, make it apply, and then I'm going to change the boundary conditions at my cell. So there are these are the cells. What I will do is that, just for your understanding, I will put it in terms of some temperature. Say for example 333 Kelvin, make it apply. I will put it for each and every individual cell. In addition to that, you may apply your internal heat generation also as a boundary condition, heat generation rate. But just for understanding, I will keep it as a temperature. So you need to apply it at each and every place. So let's keep it the same value which I had, the 333 Kelvin. Let's make it here. Let's this is again 333. Okay, one more time I will just make it nickel over there, make it this one also same, make it nickel over here, close this, then make it nickel over there, close it, the fourth one also make it nickel over here, make it apply. This one also you need to do the same, put it nickel over here, then for 14 also make it nickel over there, put it 333. Just check if I put it 333 over here. Yeah, it is there. Then in 14 I just put, I guess, yeah. Then I have 15, I will put it again, say temperature 333, put it nickel here, close it. Let's have this one, temperature, I put it nickel, say this is 333, make it apply, then close. Then one more time, put it nickel, temperature as 333, make it apply, close. Here also we'll do the same, nickel, temperature 333, sorry, make it apply, close. If you are considering more number of cells, you need to put the boundary conditions at each and every place. So that is one of the tedious task when you have more number of cells which are present in your system. Yeah, put it nickel, say temperature around 333 Kelvin, make it apply, close. Let's take this one, nickel, temperature, put it 333 Kelvin, make it close. One more time, make it this one, temperature, put it 333 Kelvin, put it nickel, make it close. Wherever we are applying boundary condition, there we are selecting the solid material which we had specified, that is nickel. So we'll put it 333 Kelvin over here, make it apply, make it close. And the last one we'll have this one, that is again for temperature, we put it 333 Kelvin, make it apply. Sorry, this is nickel, we'll make it apply and close. Just check it here whether you specify. Okay, yeah, we already specified. So in this way we are done with the applying boundary conditions over here. We applied boundary conditions on inlet, we have boundary conditions on the wall, cell wall only, not at other place we have put it. So reference values, we will start it from inlet. We need to tell the computer from where to start. So we'll put it, we tell the computer from where to start. So put it inlet, okay, make it inlet. Reference zone will take it battery pack. Then go to your initialization, put it from the stand again at inlet over here, make it initialize. Okay, now go to your calculation activities, put this auto save to around 20. Then go to your solution animation. You need to set the animations over here. Say for example you want to watch the temperature. So where you want to watch the temperatures, inlet, I want it to wall, I want it at outlet. So I selected all these three. In that case you may select the float option, so as to visualize the scale in a proper way. You can make it save display, make it close this. If you want, you may change the name of it, say as a wall temperature, make it okay. And then one more time, if you want some different simulation, you can put it, let's say new object. Instead of like temperature, if I want velocity over here, now where I want say for example at inlet, I want it for outlet, and I want it for wall. You can select the option. Instead of exponential, make it float, close this, make it save display, and you may close this. Okay, just a minute, you need to select all of the contours. Okay, so I selected this, make it compute, and just close. So this will be your second one. You may put it velocity if you want, make it. So we are done the two things. Now it's time to generate the simulation. I will take it around say 10 first, make it 0.05, or let's say 0.5 first here. Now depending on we say what you're going, if you are selecting the adaptive time step, if you are selecting the fixed time step, so accordingly slightly the things will change. We are going for some safer way so that there should not be any problem of current number, so that's why I put it somewhere around 0.5. And now I am going to run this simulation. So let's click on the calculate and just see how the things are been visualized on your animation window. So this was one of the thing which we are observing as a velocity magnitude. We are more interested about how the temperature variations are been there. So this is a scale residual which you are right now observing. Now another thing which, yeah, we are going to see the temperature which is been a way like this. So we have specified this one as an inlet, this one as outlet, and according to this we say how the fluid flow, that visualization will also take place, how the fluid is moving from inlet to outlet, that also been observed, and the temperature is distribution along the cell is also been observed over in this particular window. So this is how you can run the simulation, and this is we have run it for initial time step size of 0.5. You may run it for 100 number of time step at the same initial time step size. You can see the variation of temperature which has been taking place. So apart from that, if somebody wants to be interested in velocity, that can also visualize by one of the way. I will be more interested about these the static the wall temperature which has been there over here. So if you want, you may click one more window which is related to the wall temperature. So what you need to do is you need to go to the solution animation, click out the new object, and in this case instead of temperature, what I will do is a wall temperature. You make it here, select inlet, outlet, and the walls over here. So we will be in position to visualize the wall temperature also. So make it float, make it close, and make it save display. Close this window, and you may set this temperature as the wall temperature. Make it okay. Okay, just a minute. Okay, we already specified this as a wall temperature. So third one we need to specify with a different name. Yeah. Okay, so third one will specify with wall. Earlier by mistake the static temperature we have specified as a wall temperature. So what you may do is you may change this to say static temperature instead of wall, because it was a static temperature. If you see here, it is a static temperature. So make it like this. So I change the name. Now one more time what I will do, I will go on to initialize it, make it initialize. Okay, just a minute. compute from again inlet, make it initialize. Yeah. Okay, so once initialization is done, you come to run calculation and again say, now earlier I put it for 10, now I'll put it for 100, or let us say for 50 first, and let's start. So now it will start from again 0 because we have initialized it again. So your residual window will again start from 0. You can see the iteration also started from 1. So this will take time somewhat. Okay, it started again from 0. So this is the scale residual. Let us start from 0. This is static temperature. This is your wall temperature, which you can see. So how the temperature distributions are there, so that you can visualize. Somehow you are able to see the heat has been coming, it is taken up by the fluid which has been present. In between that you will see some gaps, so that fluid is taking heat away from the cell wall. So we'll run it for somewhere around 50 time step, and then we'll see the same with the help of the window which is in the post processor, how it looks like in post processor. Right now we are quite been better position to visualize this as contours of wall temperature, as you can see. So depending on how much flow time you want to compare, maybe with respect to your experimental one, you can run this for as many time steps as possible, so as to visualize in quite better way how the fluid flow simulation is taking, how the fluid flow has been taking place in the battery pack. So let's wait to complete this, and then we'll shift to the post processor to see how the temperature visualization that can be done. So this is how the static temperature that can be observed. So around 11 time steps have been remaining. Once this is completed, you go back to your workbench window and save the work, so that you can start the same work again from the last time step. So once this is completed, you will see a calculation complete message. Click on that. In addition to that, you may go to the animation here and playback. Say we are run it for 50. You can see the static temperature how it is varying from. So let's see. These are very only 50, so that's why not much variations will be observed. You can see the wall temperature also again. You can run it, or even you may keep it at lower speed also. How this is varying, that you can just check with lower speed also. So in this way the simulation can be observed. Okay, so I will close this. We'll go back to workbench window, save the work. Now I will open the result window. Okay, so you can now open the result window. So what you want to visualize, we will want to visualize this pack. Okay, so first of all what I will do is I will go to the volume rendering and will select the temperature because we have specified one of the parameter as a temperature. Make it, instead of global you may specify user specified. Say we have taken it 298 Kelvin to around 333 Kelvin, so I will put the same scale which was been available there. Yeah, you can see some variations out here. Apart from that, uh, if you want you may have one more contour which will be related to your velocity. So select the velocity out of it, make it apply. So you may see the velocity contour also out of which. So in this way the simulation can be visualized for your battery pack. You may have this volume rendering just for your temperature. If you want a better scale on this, you go to the legend view. Instead of go to the appearance, make it fixed number of values. If you want uh, 11, say for example, you may put it. You can change the aspect ratio here, making it better visualization. Where you want it, you may say left, center, you may keep it like this. So in this way this can also be varied. Apart from that, if somebody wants to visualize the flow time and other thing, you can select the time value over here. Say location is left, say left bottom, you will see here, make it apply. In addition to that, if you want some time steps to visualize, click on this, click on the time steps over here, put out the location, let's say center and maybe at the top, make it apply. So this will be available here. So in this way the various things that can be visualized. If somebody wants to prepare some charts out of it, that can also be done. Only thing you must know is the location of each and every individual cell. So how to do this, let's keep it line 1. So what should be the location? If you remember the location which you are taken, you are taken 92 mm in the respective direction. So you need to plot a line. So let's make it, this is point 092 over here. Let's apply. So you can see the line has been drawn here. Now I want this line to be shifted in Z direction. So let's make it 0.01, make it 0.01. Just check it how the line goes. It is goes here. If I don't want it at this location, maybe I can put it 0.05. See where the line goes, it is slightly here. Instead of that I will make it 0.004. It will be slightly below. Okay, sorry, 0.004, it's slightly below. Or if you take it 0.003, take it 0.003 like this. So it will be slightly below. Same way, if I want temperatures on this line or near to this line, I can plot it. Okay, so let us suppose this is one of the line which has been drawn and I need temperatures along this line. So what I can do is I can go with the chart option available, make it here, go to the data series, select here as a line 1 and your x-axis put it your say x, y-axis put it your temperature and let's make it apply. So we'll get such kind of chart which x-axis shows you the distance and y-axis will show you the temperature along the line. So this way the charts can be prepared. If you want to prepare, you want to know the temperatures along this line, accordingly you can put the line in vertical direction and accordingly the respective temperatures can be measured. So I hope this is understood. Thank you.